Yeah, in previous lecture, we studied that the general formalism of tight binding model is that Hamiltonian is the atomic Hamiltonian plus potential difference, and in this case, the crystal Hamiltonian, the wave function of the crystal Hamiltonian can be written like this for reciprocal for Bravais lattice vector exponential I k dot r and phi r minus r, where the phi r is the summation of the localized wave function. Here Bn is the coefficient and psi nr is the atomic wave function, localized atomic wave functions. And from this lecture, then I will apply some basic calculation of simple crystal structure by using the tight binding model. Application of tight binding model. And I will investigate for the simple crystal structure in S-band. Simple crystal structure and only S-band. Then the P-band or D-band can be calculated also. And S-band means that in the orbital angular momentum L equal to 0, and it is non-degenerate. It is non-degenerated because a single energy occupancy. And for P-band case, because L equal to 1 and there are 3 degenerated state, 1, 0, minus 1, it is a triply degenerated. And also D-band L equal to 2, there are 2, 1, 0, minus 1, minus 2, and it is a 5 degenerated. Therefore, in the P-band or D-band, it needs the 5 equation, the degenerated level should calculate explicitly by using the tight binding model. And also, there are 6 by, for example, in the D-band calculation, there are 5 by 5 secular problems. And for example, and for D-band case, because there are 5 degenerated state, and therefore in this case 5 times 5 secular problems. And D-band, S-bands, and because in this case then S-band is 1 non-degenerate, and the D-band 5 degenerated levels. In this case then there are 6 by 6 secular problems, and for example D-band and S-band, because S-band is fully occupied and the D-band partially occupied band case, and in this case 6 by 6 secular problems. And also SD mixing or the SD hybridization should be included. And here let's calculate for simple crystal structure in the orthorhombic structure. Only S-band case. Orthorhombic crystal structure is that the crystal structure is like this. There are A, B, C lattice parameters, and the lattice parameter A, B, C are not equal with each other. And the A1 is that AE1 and A2. A2 is that B, E2, and A3 is that CE3. Here, VR is the actual crystal potential. And V0R is the potential of isolated atom. Isolated atom. Then the crystal Hamiltonian, in tight binding model, the crystal Hamiltonian is that atomic Hamiltonian plus and the deviation of the potential. And the deviation of delta V means that the real potential minus and the atomic potential, isolated atomic potential, it is that delta VR for modified potential difference. And we should solve the Schrödinger equation, and H psi kr equal to energy and psi kr. It is the eigenvalue problem, and also the psi, the wave function should follow the Bloch theorem, like that it is a summation with reciprocal lattice, not reciprocal, but is Bravais lattice exponential I k dot r. It is a summation with the Bravais lattice, and phi r minus r. Here phi is that summation of the atomic wave function. Here, let's substitute this wave function to the eigenvalue problem. The Hamiltonian, the first term is the atomic Hamiltonian, and the atomic Hamiltonian phi is the summation with r and exponential I k dot r, and phi r minus r. And the potential difference is that VR minus V0R, and the wave function summation with r exponential I k dot r, and phi r minus r, and energy epsilon k, and summation with r exponential I k dot r, phi r minus r. It is the direct substitution with this equation. And also, to calculate the expectation value, and let's integrate like this complex conjugate r in the atomic Hamiltonian summation with r exponential I k dot r phi r minus r dr. This is the first term. This first term only survives at the reciprocal at the on-site, because the integral with the nearest neighbor is very small, and here anyway, and I will directly integrate in second term phi star and potential VR minus V0R, and summation with r exponential I k dot r, and phi r minus r dr. This is a second term of this potential, and finally it is energy eigenvalue, and also here is that integral phi star r epsilon k summation with r exponential I k dot r and phi r minus r dr. Here, as I said, this atomic Hamiltonian term it only survives at the on-site potential, because the integral between the nearest neighbor integral is very small. Only survives at r equal to 0 and on-site. In the other integral, nearest neighbor interaction is very small. I will say nearest interaction orbital overlap integral orbital overlap with nearest neighbor is very small. And finally, this one has the energy eigenstate. In the same way, in the same way, this term, the final term only survives the epsilon, because the integral between the r and nearest neighbor interaction is very small. Then we should calculate the energy, calculate the potential here. This potential we should calculate, and therefore we should calculate this phi star r VR minus V0 r summation with r exponential I k dot r phi r minus r dr. This is a potential term, should be calculated, and we should calculate the on-site interaction and the nearest neighbor interaction. And for example, it is on-site r equal to 0, but in the nearest neighbor case, and r equal to Bravais lattice vector plus minus a e1, and also plus minus b e2, and plus minus c e3. This is nearest neighbor interaction, and not exactly the nearest neighbor, but we only consider for the three-dimensional space, three-dimensional Bravais lattice. And also, therefore, the on-site interaction is that phi star r and potential difference minus V0 r and phi r dr. It is the r equal to 0 case. And the other case, there are we should calculate this kind of Bravais lattice vector. And in this case, in E1 direction, let's calculate the E1 direction, and phi star r and V minus V0. This is potential, and also here exponential I k dot r. Here it is exponential I kxa plus, because there an r vector in the x direction is the plus minus a, and also exponential minus I kxa. It is this term, and also phi r plus a1 vector. Here a1 vector means the plus minus a e1 and dr. The secondly, and in the y direction, component, it is the phi star r v minus v0 exponential I kyb plus exponential minus I kyb, and the phi here r plus a2 dr. It is a y direction, and the g direction case, and the phi star r, and the v minus v0, and likewise exponential I k g c plus exponential minus I kgc. It is a g direction case, phi r plus a3 dr. Okay. Then in this case, we do not exactly know the potential difference, but here we can treat this potential difference as the parameters, because we do not know the exact potential like this. We do not know this one, and anyway, and the potential difference is the case by case, depending on the crystal structure and the interaction or the anyway, we treat it as free parameters. For example, and here this one, let's define that this first term, let's define it as minus b, and also here anyway, and this term means that exponential and minus exponential, and it means that it is cosine. It is a cosine function, and the cosine function is the real value, therefore integration does not take into account. And anyway, and therefore let's define the parameters. And the b is that minus integral phi star r v minus v0 phi r. It is an on-site interaction, and tx means that transfer of electron, and the transfer means that minus phi star r, and v minus v0 and phi r plus a1. It is the interaction between the along the ax direction. It is x direction, and also the integrand, the exponential, two term is the cosine function. And also likewise the ty is that minus phi star r and v minus v0 and phi r plus a2. It is a1. It is a dr, and it is a transfer integral along the b direction, and tg is that transfer integral along the c direction, and phi star v minus v0 phi r plus a3 dr. Here we treat this equation as a free parameters, and because actually we do not know the exact form of the potential difference, therefore it b, tx, ty, tg is not exactly determined, but it can be treated like the free parameters, can be compatible with the experiment. From the above equation, and this equation is the real tight binding interaction, and therefore when you make summarize this one, and the epsilon energy eigenvalue is that E phi and also minus b. It is a free parameters, and here exponential term is that minus 2 cosine t2 2x cosine kxa. The 2 cosine kxa comes from the exponential I kxa plus exponential minus I kxa. Therefore, likewise, then the minus 2 ty cosine kya minus t2t to tg cosine kgc, not kya but kyb. Therefore, And when I make a diagram and the actual potential, the potential with respect to R, and there is a localized potential. VR is the real potential, and also it is a localized potential, and the atomic potential, localized atomic level, their energy is quantized. For example, n equal to 1, n equal to 1, and n equal to 2, n equal to 3. Like this, there are quantized energy level. But in tight binding model, and this localized energy band can be spread it out. And for example, in the energy, let me see the energy versus 1 over R. Then this atomic level corresponds to the single eigen level for because x-axis is the 1 over R, therefore it is the zero limit is the far distance. It means that because far distance, the crystal Hamiltonian completely coincides approximately anyway, and approximately can be considered as the atomic Hamiltonian. And therefore, but in real cases, but when we think about the potential difference, and because of this cosine term, and it spread it out like this, energy level spread it, and also this energy level also spread it, and this level also spread it. Therefore, in this case, then there is a band crossing. Then because there are band crossing region, band overlap, and it is due to the level broadening. Level broadening is coming from the interaction between the nearest neighbor interaction, and it is one simple example of tight binding model in the orthorhombic crystal structure.